Hello and welcome to another video in our series on introducing statistics and statistical inference. Today we are going to look at the t-test for independent means. We call this topic 8. We've done our discussion. Today we're just going to do an example by hand and slowly walk through the calculations. The book we're using, as always, is the Statistics for Psychology book. Just wonderful explanations, super clear. We're going to go to page 309 and look for number 18 here. A little wordy, so let's take our time. Remember, you can always pause the video if you need to. 20 students randomly assigned to an experimental group received an instructional program. 30 in a control group do not. After 6 months, both groups are tested on their knowledge. The experimental group has a mean of 38 on the test, estimated standard deviation of 3. Control group, who didn't receive the instructional program, has a mean of 35, estimated standard deviation of 5. I want to use the 5% level to see if the program improved the test results. All right. So we want to sketch it. We want to go through the hypothesis testing steps according to this book. And we're not going to answer C in terms of writing it out. As we go, our explanation, our discussion will be obvious from C, and you can summarize that by writing it down and taking notes as you may need to. All right. So it should be hopefully clear that we have two separate groups independent from each other. The first group gets the instructional program, then the 20, and another 30 people do not. These are not the same people. These are two separate groups of people. So I'm in the independent groups situation, testing the means for independent groups. So let's start. Let's just number this here, name it appropriately. Let's just be thorough and list our two populations as the book suggests that we are comparing. So population 1 will look at people that receive the instructional program. So since this is our first example where we're slowly writing everything out, going through the calculations, it's best to take your time and be thorough. And then we're comparing that to population 2, the control group, so to speak, the people who do not receive the program, not receiving this treatment of sorts. Instructional program. All right, so now my null hypothesis versus my research hypothesis. Well, the research hypothesis is sort of what I'm hoping for, informally speaking, and I'm hoping for an improvement in the average test results. So I'm hoping that receiving the instructional program improves the test result. Did they say what they were testing for? Assigned, control group, both groups are tested on their knowledge. So it improves your knowledge according to some test. And then the null hypothesis is, of course, that there is no change. Or in other words, that the difference between the two is 0. We are going to look at the distribution of the difference between two means, and the null hypothesis is going to be a 0. Again, I guess similar to the dependent means situation. But here I have two separate groups, two independent groups. So coming up with my comparison distribution is a little different. Comparison distribution. Trying to write as clearly as possible here. Which will be the comparison distribution will be the distribution of the difference between the means. All right. So on the surface, it looks similar to the dependent means situation, but it's not. It's not quite the same. For the mean of this distribution, we'll call it mu diff. That under the null hypothesis will be 0. However, if I'm trying to approximate the standard deviation of this, sorry, my P's do not look good today. I don't know why. Let me just restart that whole word. Approximation of the standard deviation for this distribution, that is where the complexity in the calculation comes in, where I have to think about what we're doing here. So let's just scroll up here a little bit to give ourselves some space. So let's just summarize the two samples. I have 20 in the first and I believe 30 in the other one. The control group, they're tested. The experimental group, the treatment group, so to speak, has a mean of 38, estimated standard deviation of 3. Okay, let's put that in here so we remember. So our mean is, I just read it, 38. And our estimated standard deviation is 3. Degrees of freedom for this one will be 1 less than the sample size. For our control group, what were the statistics? 35 mean, standard deviation of 5, estimated. 35 mean, standard deviation of 5. Degree of freedom here will be 1 less, 29. So we have two groups. And our assumption in this t-test is that the variance is the same throughout. We want to get the best estimate for the variance throughout the groups. So first of all, our total degree of freedom, we'll say here degrees of freedom total will be the sum of the two. Let me just number these. 1 and 2 put together. Then we have our 19 plus 29 for, of course, 48. So I remember that when I have to go to my table. Now we're going to pool the estimated variances together. Pooled variance. Now each one has a variance here, right? This is the standard deviation estimate, so I would square it. So this one is 3 squared and this one is 5 squared. However, they come from different sample sizes. I'm going to weigh them according to the degrees of freedom, which is directly related to the sample size. So I'm going to, let's just write this out and let's show the formula that we're looking at here. So we're at 8.1 here, where to get the pooled variance estimate, pooling both samples together to get the best variance, I'm going to combine the two variance estimates from each sample, but I'm going to weigh them according to the degrees of freedom, which is directly related to the sample size. So that's the formula we're going to use. So the first sample has a degree of freedom of 19. So it sort of has a weight of that fraction that it contributes. And I'm going to multiply that by, I'll write here 3 squared, the standard deviation estimate squared. And then the second sample will have a weight of its degree of freedom over the total. And I'm going to multiply that by its variance estimate squared. So let's do a calculation there. See something in our calculator. 19 divided by 48. Feel free to do that with me. I'm just going to write a 9 there because 3 squared is so easy. Plus 29 divided by 48 times 25. What do we get there? We should get, if I round it, 18.67. And again, like I always say with these hand calculations, we accept the fact that we're going to round to make things manageable because we're doing it by hand. In reality, you would use software to aid you in the calculations, and then you can be perfectly accurate at all times, and there's never any issue. I'm not going to do a millions of dollars study by hand and run the risk of rounding errors, creating slightly incorrect conclusions. This is just running through the calculations so we learn the process. So I'm not going to obsess over rounding errors here. I'll just round everything as we go to 2 decimal places, knowing this versus reality. So now let's just see here if we have a formula. I do, a 2 here, my formula sheet. We don't have to memorize these. We have a formula sheet to help us. So I now want to estimate the variance for each of the groups as accurately as I can. So I'm going to take this the same as 7.5, take the best estimate for the variance, which is the pooled one, and of course divide it by the corresponding sample size. So my variance estimate for the distribution of means, because that's what I'm looking at. I have a sample more than one, so I have to look at the distribution of means for that sample is going to be the pooled variance, oops, ugly 8 there, divided by the sample size of 20. And I'll just write the other one as well. The variance estimate for the distribution of means for that population according to the sample size, I take the pooled variance estimate and divide by the sample size. So let's see what we get there. Do a little calculation. 18.67 divided by 20. For the first one, we get 0.93. Let's do the second one. Doing everything by hand is always going to be a little slower, but that's okay. It gives us time to get used to the process and the calculation. And we get 0.62. All right. So now, ultimately, I need these because I am looking at the comparison distribution as the distribution of the differences between these two. Now, for the mean, arithmetically, it works the same and will be a difference as well, which is why it is 0, according to the null hypothesis. However, regardless of if I add or subtract the two, the variance is always additive. So my variance estimate for the difference between these two is the sum of these two, because worst case the variance could be the worst in both and then giving me a bigger variance. So I always add the variance and I get 1.55 in this case. Then the last thing I have to do, of course, for our, let's go to the formula here, for our t statistic, we have to divide by the standard deviation. We have the variance, so, oopsie, where's my pen? Pen. I can't get my pen. There we go. Pen, there we go. So for our estimate of the standard deviation, we then take the square root of that. And of course, disclaimer, ignore rounding. If you have a good number of decimal places, you're not going to be fundamentally wrong too far away. But we understand what we're doing here. Let's show we're just doing things by hand, so our numbers might be a little off because of the rounding. That is not how you would do it in practice. You would make sure you're perfectly correct before spending so much money on these studies. Oops, I need to have two equal signs to tell MathBot what I want. There we go. And we get 1.24. All right, so those two are the ones we need. All right, almost there, but this one is a little bit bigger. So now we're going to go, you can do your observed first. Let's go observed. Observed, let's call it T observed. That's going to be, per the formula, very similar to before. You have essentially the difference between the two means minus sample means minus the difference between the two population means, but that's 0, so it's not included here. So it does follow this, like 7.7. It does follow that sample minus population. It's only that the population value is 0. So we can write that in here. Difference between the two means 38 minus 35. So don't think that we're not doing the mu part in this formula. We are. It just happens to be 0. So let's calculate that. And we have, oh, I need brackets. Not that I need 38 minus 35, but you know, we'll be thorough. Divided by 1.24. We get a 2.42. Now we're comparing that. I'm running out of space for my sketch, but I think we can squeeze it in. We're going to compare that at a 5% alpha. Our T cutoff is going to be, remember, our degrees of freedom will be 48. So we have to go look. Let's visualize it first before we go look. Squeeze it in here. Running out of space a little bit, but that's okay. Ooh, that's a nice bend in my curve. That's a little wobbly. Let's fix that. Try and be smoothish. That's good enough. We're going to take it. So we're centered here at 0. This is the distribution. Yeah, you know, you're right. It's not very good, right? This is the distribution of the difference between the means. So I have some symmetry here, which means I'm going to have to do it little by little. That's okay. Trying to not obsess over this, but it's hard. So for 5%, now remember this is one-tailed, because if I take mu1 minus mu2. I'm looking at a greater than necessarily. Now, admittedly, you can argue that the question didn't say we're looking for an improvement, just what should they conclude. So you can set this up either way. It's unfortunate they don't really specify if they're testing for improvement or just difference. But usually if you have an instructional program, something extra people undergo, you're doing that with the intention of improving the measured variable. So that's why we went with improvement. So we're only looking at on the right. Whoopsie. Where's my hand now to move this? So we're over here, 5% in the tail on the right, T cutoff, and we look it up with our data tables because we're doing everything by hand. We're looking, whoa, hello, not go that far. We're looking for a degree of freedom of 48. Now we don't have that, so then what we tend to do is just pick the closest one. So we are sort of rounding things in a way there anyway. 5% I believe is the middle column here. So we're going to use a 50, 1.676. 1.676. And again, with software, you don't have any gaps there, so you would know exactly. 1.676. And then we're comparing our observed t-score, which sits out there, further to the right. So we're ready for our conclusion. So since t observed is greater than t cutoff, I'm just going to move this a little bit to the side so I have more space. We reject the null hypothesis in favor of the research hypothesis. And we say the evidence is strong enough to suggest that the instructional program improved the knowledge or the tested knowledge, however they measure that. And there we go. So focus on the similarities, focus on what's different, and then there's not that much that's actually new. Of course, it's very important to identify which t-test, which situation am I in. Independent means the issue is in correctly estimating the standard deviation for the distribution of the difference between two means. That is the part that is really different in the calculation process. And then once I have that, everything else at the bottom here and how I make a conclusion with the t-distribution is all very familiar, I hope. All right, that brings us to the end of this example and this video. Hopefully that made sense. Let me know if it didn't, if you have any questions as always, and we will chat again next time. Thank you.